Hello and welcome to this mathematical presentation related to turning points. We're going to calculate the maximum and minimum turning points to various equations given. This was actually a live lecture delivered over the internet, but below I've outlined the contents of the entire presentation. We commence with an introduction, which includes an overview of maximum and minimum turning points and also points of inflection. Next, there is an outline of the four-step method that we're going to use to solve for the turning points. And we have example 1, equation given here, where we determine one turning point. Next we have exercise 1, again it's fully worked through. Here we find two turning points. Next we have question 1, very similar to example 1, and the full solution to finding the single turning point is shown. And question 2a, equation shown here, solution to find the two turning points is shown. Question 2b, cubic equation shown here, we solve this for two turning points. And then finally we have example 2, which is essentially a brief overview of a turning point practical application, where we find the maximum volume of a specified container. So there is actually a separate presentation which reviews turning points of practical applications in much greater detail. And for your reference, here are the approximate start times related to the various sections contained within the presentation, hopefully to aid your ease of access through the presentation, but please note all times are generally rounded to the nearest minute. For reference, here's some terminology to be aware of. This presentation essentially calculates turning points, often referred to as local maximum turning points or local minimum turning points. These turning points also come under the umbrella heading of stationary points, but stationary points also include points of inflection. And just note the word inflection can actually be spelt several ways. This is the traditional British spelling, but often these days it's spelt using the American spelling. In last week's lecture, I went through the process of basic differentiation using standard forms and standard tables. We looked at a little bit of application last week, finding gradients at points on curves. I'm going to take that a stage forward this week. We're going to have a situation where we're going to look at equations, where we're going to find what's called turning points of the equation. So on the diagram you're seeing in front of you here, the turning points here would be point P at the top of the curve there and point Q at the bottom of the curve. Now the point P is defined as a maximum turning point, and what we kind of mean by that is that if you take a point just before P, so take a point here on the curve before P, if you draw the gradient to that on the curve like we did in last week's lecture when we were introducing differentiation, you'd get what's called a positive gradient. That'd be a positive slope for that particular line there. If I was to take a point closer to P and I draw a tangent to that point, we can see that we still got a positive gradient, but it's obviously reducing in its gradient value. If I get closer to P again still and I draw another tangent to the curve there, we can see the gradients reducing still further until I get to the top of the curve at point P, and if I draw a tangent to point P I now get a horizontal line because we're at the top of the curve, so the gradient is 0. If I was to take a point on curve after point P, say here, and I draw a tangent to that point, now we see we've got a negative slope, and it becomes increasingly negative the further away we take our values from the right side of P. So that defines a maximum on our diagram, a maximum point at P, where the gradient is decreasing in its positive sense to the top of the curve at P, and it's increasing in a negative sense after we go past P. That's defined as a maximum. And if we look at point Q, same kind of thing here, if we take a point before Q on the curve, we draw a tangent to that point and work out the gradient of that line. Well, obviously it's a negative gradient there. We take a point closer to Q, we work out the tangent of that point. There we'll find it's a decreasing negative value until we take a point at Q, draw a tangent to Q, and we find we've got a horizontal line again. As soon as we move past Q here, start drawing tangents to the lines, we go back to a positive gradient. So this point is defined as a minimum point Q is a minimum because the gradient before Q is decreasing in its negative sense and it's increasing in its positive sense thereafter. So that's like the definitions of what's called the maximum turning point, as point P in this case, and the minimum turning point is point Q. So those are 2 points on the curve. Sometimes we're very interested in, because in a context, for example, velocity time context, that might relate to the maximum acceleration in the system and the minimum acceleration in the system. We might be interested in those particular values. In other contexts, it might be the maximum volume of a component or a minimum surface area of a component. You'll see later on with exercise questions that you'll have those kind of parameters given to you where we're interested in finding these maximum and minimum points at these kind of points here on the curve. There's another curve here. We can clearly see in this curve we've got a maximum here at this location and a maximum here, so 2 maximums here. We've got a minimum here, a minimum point shown there, and these points in the middle are actually called points of inflection. Slightly different to the maximums and minimums in that if you take a point to the left of this point here, I'm highlighting, and we draw a tangent to the curve, that's obviously a negative gradient. If we take the actual point there, what's called the point of inflection, and draw a tangent to that, that would be 0 gradient because it's a horizontal line. But if I take a point after the point of inflection and draw a tangent to that curve, we can see it's still a negative gradient. So in this case what we've got is a 0 gradient, but we've got the same gradient before and after, the same sense of gradient. In this case it's negative before the point and it's also negative after. And the same approach we can see over here with the other point, this one here. Again, if you look at a point before the point of inflection, we've got a positive gradient. If I take a point there, and if we take a point after the point of inflection, I've still got a positive gradient. So they're classified as points of inflection as such. And all these points, turning points, these maximums, minimums, points of inflection, they're often called stationary points in some textbooks. All right, stationary points, there's a name for them. So maximums we've got up here. This is a maximum turning point. This is a minimum turning point. And as I said there, we've got those points of inflection that sometimes crop up. Mainly it's maximums and minimums we'll be looking for in the work that we're going to do here. Okay. And for ease of reading, I've just included this enlarged slide of the previous discussion. I just slightly reworded this point of inflection section. What I'm showing you here is on your next page of your notes is the process we need to use to determine our maximums and minimums and sometimes points of inflection. So it's a 4-stage process as I've outlined it there, and I'm going to try and rigidly stick to those 4 stages to give you a kind of coherent process to follow every time. So I've blown up on the next slide these steps. Basically there are 4 steps, and we will be referring to the standard differential table that we used last week in our standard differential questions when we were introducing the topic. So we will still be using that table, but primarily we're only going to be using the polynomial function, the ax to the n, which differentiates to anx to the n minus 1. We spent quite a bit of time on that in the previous lecture. That's really the only function we'll be using today in this work. But I'm going to outline the process of the 4 steps here, a bit more detail on the next slide. So this is the way we find the location of these turning points, the maximums or minimums, and define whether they are maximums or minimums. We need to know both of those characteristics. So the first thing we're going to do in step 1, we're going to be given some function. Y is some function of x, so y is equal to 3x squared, for example. And we're going to find the first differential as we did last week. We're going to find the dy by dx using our standard differential tables. Don't forget sometimes the questions are written as function dash x. We talked about the 2 different types of notation last week. Dy by dx is the same as function dash x, first differential. So we're going to differentiate as we did last week in the first step. In the second step we're going to equate the differential, the dy by dx, to 0. Okay, now we're going to solve that equation, a little bit of an algebraic arrangement there, and sometimes we might find in that step that we end up with a quadratic form. So when we undertaken our differentiation of our standard equation, start off with a cubic, for example, as your function of x here, you may end up with a quadratic to solve in step 2. So we need to be aware that we might use factorisation to solve the quadratic if it does crop up at this stage, or we could use the quadratic formula shown here. We've used that before many times now. So in step 2, it sometimes can be a simple rearrangement, algebraically rearranging the equation to solve, or sometimes we may have to use the quadratic formula or the factorisation method. And there'll be 2 answers, of course, if we get to that stage, and usually only one of them is relevant to the problem. So step 2 sometimes can be very simple, or something that can be quite complicated really. In step 3 here, what we're going to do is substitute the values of x we found from step 2 into the original equation again. This is because we want to define the turning point. In step 2, what we do is calculate the x value of the coordinate, so we know the x value on the horizontal axis, but we also need to know where it is in the y-axis. So once we found the value of x from step 2, we put it back into the equation we're given in step 1, and then we can find where the y value is, and that defines the coordinate. So we're trying to define the coordinate of our turning point or our stationary point in step 3, so we define it in 2 dimensions. So that then says we've got a maximum or minimum in a particular position on our xy diagram, but at this stage it doesn't tell us whether it's a maximum or a minimum. Okay, we could go away and produce a graph of the function of x, and we could see whether it's maximum or minimum, but that can be quite time consuming. So we're going to show you another way of finding if it's a maximum or minimum, and that's where step 4 comes into use. And this is step 4 shown graphically. Again, this is in your notes, it's shown a bit enlarged here. So what I'm trying to show in the first curve at the top of the page there, this is where we would have our y is equal to some function of x plotted. So that's the basic equation that we're given in the question. If you plot it, that's what it would look like. And if we plot it, we can clearly see here we've got a maximum at point A, we've got a minimum at point B, and we've got a point of inflection at point C, looking back at our definitions on the previous slide. So we can clearly see them, because if we didn't have the diagram, we wouldn't know that. So we're going to use this process called successive differentiation to find whether they're maximums or minimums. And the next graph below here, this is the differential. This is where we've differentiated the above equation. This is our dy by dx equation, just to make it clear there. Okay, that's dy by dx. So we've differentiated. Now don't forget, going back to the initial presentation we had on this, when we're finding the differential, all we're doing is finding gradients at points on curves. That's all differentiation is doing here. So this is trying to tell us what the gradient is as we go from 0 through the values of x on the horizontal axis. So looking at the diagram at the top of the page, we can clearly see if we draw a tangential line through point A there, that would be a horizontal line. So that would be 0 gradient. And that's exactly what this is telling us in the first differential. We have a 0 gradient here. For the minimum at point B, again, if I was to draw a horizontal line, tangential, it would be a 0 gradient there at B. We can see it's a turning point there. And again, if I look down at the dy by dx, I can see that I've got 0 gradient again. And then finally at point C, we've got a point of inflection. Again, if I draw a tangential line to C, it'd be a horizontal line. And there's my 0 gradient again, which it shows on the dy by dx curve. So if I didn't have the original top curve, I could actually find where my turning points are simply by differentiating and equating to 0 and solving the equation, which is the step we used, step 2 in our process. But if I want to know whether they're actually maximums or minimums, I need to then differentiate one more time, because this equation here, dy by dx, doesn't tell me if they're maximums or minimums. It just tells me where I've got 0 gradients. So it tells me where I've got turning points, that's fine, but it doesn't tell me what they are. And it may be that I'm looking for the maximum or I'm looking for the minimum in the context of the question. So that's why we produce what's called the second differential, written in this format, d2y by dx squared. That's a conventional format. If you're using Newton's notation, it would be written as function double dash x, because the first differential is written as function dash x in Newton's notation. But I predominantly use the Leibniz notation, d2y by dx squared. So this is just this equation here and differentiated again using our standard tables. What you'll find now is that if the value from the second differential for a particular value of x that we've calculated, put the value of x into the second differential and it's a negative value, that relates to a maximum on our initial y is equal to function of x curve. If the second differential value, a given value of x, so that was at the value of x is equal to 1, we've got a negative value, the value of x is equal to 2, here we've got a positive value on our second differential, that means it's a minimum on our curve. And if the value of the second differential is 0 and we put our value of x into the equation, then that means we've got a point of inflection. So the second differential is very useful in that it tells us if we've got a maximum or minimum. We don't really care about the values from the second differential. I don't care whether it's sort of -5 or -50. That's not really of use to me in what I'm trying to calculate. That's just looking at the rate of change of slope. It's not something I particularly want to find in the questions we're going to look at. I just need to know the sense of it. If it's a negative value on the second differential, I've got a maximum. If it's a positive value on the second differential, I've got a minimum. So this is the process we're going to go through to find our turning point. So it's a fairly complicated process, but it is a sort of repetitive process. Once you've done it for a couple of questions, it's the same thing over and over again. What changes the functions and perhaps the complexity of solving the equations, but the basic technique is the same 4 steps over and over again. So that's what I'm going to try and look at now, show you an example of how this process is undertaken, and then we're going to spend the time doing as many questions as we can here. So this is example 1 in your notes. It's a fairly straightforward question here, but this is it. This is the process. So in this particular question, we're given an equation. It's a quadratic equation here. Now I've plotted this because I wanted you to actually visualize this. In most of the questions, we won't have the diagrams. It's just in the examples and the exercises we've got the diagrams for illustration, but most of the questions you will not have the diagrams, so you're totally dependent on the differentiation process to find the maximums and minimums in the questions. But anyway, this question has got a quadratic. Y is equal to x squared minus 4x plus 4, and it's plotted on the diagram on the right hand side. Now we can clearly see that we have a minimum value in this particular curve. It's obviously a bucket shape here, so we have a minimum value, and I can see by looking at the diagram here, this minimum is at 2 on the x and 0 on the y. So 2, 0 is the minimum turning point in this particular case. Okay, so I can see that. What I'm going to try and do is prove that using this method of differentiation. So the first thing we do then, given the equation, step 1 here, y equals to the x squared minus 4x plus 4. You might say, well, that's just copying the equation out of the question. Well, it is in this case, but in some questions, they're not always in that format. You have to rearrange the equations to make them y equals 2. Or sometimes you have to expand brackets on the right-hand side. So not always given in the format that's ready to differentiate. This is in this case. Now we're going to differentiate this. We're going to find our dy by dx, our first differential. Now these are all standard forms, don't forget, all sort of in the table formats. So think of that as being a sort of 1x squared of my ax to the n format, and I can differentiate that to anx to the n minus 1. So 1x squared becomes 2x in my first differential. The negative 4x, when you differentiate that, don't forget that's 4x to the 1. Okay, so again, differentiate that, that's 4 times 1, x to the 0, so that becomes negative 4 on our solution there. And then differentiate a constant, we know that always disappears. If we differentiate a constant, sometimes we think of the constant having the x to the 0 against it, but that will just disappear when we differentiate it. So our first differential is dy by dx is equal to 2x minus 4. And I've called that equation 2 in this particular example. So that's step 1 done effectively. Write down the equation from the question and then differentiate it. In step 2, what we're going to do is equate it to 0. So I'm equating the equation to 0 and just solving. The reason we equate it to 0, of course, is because we're looking for the turning point being 0. We can see the turning point there if I draw a horizontal line at that gradient there. Draw a tangential line, I should say. It's a horizontal line to that point there. So what we're doing with this step 2 is trying to find where the x value is that locates the turning point. Now in this particular case, when we make the dy by dx equals to 0, we end up with 2x minus 4. That's a very straightforward equation to rearrange. Just add 4 to both sides and divide by 2, and we can solve for the value of x, and the value of x is given as 2 in this particular case here. Now that's a very straightforward question. Sometimes you can find at step 2 we've got a quadratic to solve, so we'll have to look out for those where the quadratic equation occurs. But that's a straight linear equation. I can rearrange to solve it. So we found the value of x is equal to 2 from that step. So now we know the location of the turning point in the x direction. We can see it's 2 from the diagram. We need to find the location in the y direction, and that's where step 3 comes into play. So in step 3 here, we're going to now put the value of 2 back into the original equation. So that value we've got from step 2 just goes into the original equation of x squared minus 4x plus 4. And the values of 2 in and evaluating. That gives me a y value that's 0. And again, we can see that from the diagram that the coordinate is 2, 0 for the turning point. So steps 1 to 3 has defined the turning point. We located where this turning point is in 2 dimensions. What we do not know without the diagram is whether it's a maximum or a minimum. And that's where the final step comes into play now. We're going to find the second differential, and all that means is we're going to take the equation 2 above and we're going to differentiate it again. So 2x minus 4, again that's all standard form, differentiating 2x, that becomes 2, differentiating a constant, and that will disappear. So I end up with d2y by dx squared is equal to 2. That gives me a positive value. So from our diagrams on the previous page, if the second differential is positive, then it's a minimum. But we can see it's a minimum from the graph above. Now sometimes with this second differential you may have a function of x, so you could have sort of like 3x plus 4. So in that case we'd have to put the value of x into the equation to find the positive or negative value of the second differential. And again, you'll see that in the next example, how we handle that kind of problem. But that's the basic process, what you're looking at there. That's the same in every question we're going to look at. So hopefully we'll get used to the process we're going to use here. I've just included an enlarged version of example 1, purely for ease of reference. Here's an enlarged view of exercise 1. It's now going to be considered. Okay, so I'm going to take you through exercise 1 here. Again, I've drawn a diagram to try and show you where the turning points are, so we've got something to grapple with here. But I'm going to take you through the entire process, steps 1 to steps 4 here. Given the equation, we've got y is equal to x cubed minus 3x plus 5. That's what's given in the question. So the cubic equation, so more variation in the curve here. And we can see already there's 2 turning points. This location here is a turning point, and this location here has a turning point. That's what it looks like. So just by looking at the graph, if I was going to specify my turning points here, this would look like -1, and I guess that's 7, just by looking at the graph here. And this one here looks like it's +1 and 3. So 1, 3. That's what it would look like if we plotted it off, and we're going to use the differentiation process to try and prove that, confirm that. Okay, so let's go through the steps. First step is we have to extract the formula from the question. So y is equal to x cubed minus 3x. So no rearrangement required here. We can just simply write the equation directly from the question. That's fine. And we're going to now differentiate it to find the dy by dx. So all standard form here. So dy by dx in this case. So using my standard tables, 1x to the 3 differentiates to 3x squared. The negative 3x to the 1 differentiates to -3, and we know that constants always disappear when we differentiate them. So my first differential, give it a handle, I'll call that equation 2, and I'll call that equation 1. Just give them sort of little handles there if I need to. Those are my 2 equations. The first one's extracted from the question, the second one is the first differential, using standard tables to derive it. That's step 1. Now step 2. Step 2 says we've got to equate the first differential to 0. So just put a note there. So equate equation, I'll call it 2, 2, 0. And what this is doing is trying to find the x location for the turning point. Okay, we can see above we've got two x locations here because we've got two turning points. Let's see what the equation does for us here. So 0 is equal to, equation 2 is going to be 3x squared minus 3. I've got to rearrange the equation, so add 3 to both sides, so 3 is equal to 3x squared. Divide both sides by 3 in this case, I will get x squared is equal to 1. Okay, just think that through and dividing both sides by 3, so I get 1 is equal to 1x squared there, so x squared is equal to 1. Now to find the value of x, I need to square root. Now don't forget here, be careful with this, when you square root, you get two solutions. So x is equal to the square root of 1, so that will be plus or minus 1. Okay, positive and negative 1 if you like. Okay, so two values of x we have here, and of course we do have two values of x. We have x is equal to 1 here and x is equal to negative 1 here, so we have two values of x. So in step 2, slightly more complicated than the previous example, in that we've got to square root the answer and we get two solutions. We go now to step 3. We're going to find the y coordinates. What step 2 has done is found the x coordinates for the turning points, and there's two of them. Well, now we need to know what the y coordinates are. So in step 3 we're going to find the y values. We've got the x values, we want to find the y values. Okay, now all we do here is put the values of x into equation 1. Okay, so when x is equal to 1, y is equal to, and all I'm doing is putting the value of the x equals to 1 into the equation, so that will be 1 cubed minus 3 multiplied by 1 plus my 5 in this case. So adding those values up, should get a value of 3. Let's just check that's just 1. Take away 3, so that's negative 2, add 5 gives positive 3, so 3, and again that's what we seem to read from our diagram. And then when x is equal to negative 1, and just be careful here with the negatives when you evaluate it, that's negative 1 cubed minus 3 multiplied by negative 1, careful of that, plus my 5. And that should give us a value of 7. Just be careful with your calculations. And when you cube negative 1, it becomes negative 1, and we've got a double negative in the middle. Negative 3 multiplied by negative 1 is positive 3, and then we add 5 to that. So just be careful of your sort of directed numbers in that case. So 7. So our turning points then, we can now define them. Turning points will be x is 1 and y is 3, and in this case turning point is going to be x is negative 1 and y is 7, and that's what we gleaned from the graphical method. Of course the graphical method is not always that accurate. When you get more complicated functions, more difficult to interpret the graphical method, but in this case it was relatively easy to see. So the process we're using here has been able to find the turning point. So those are the locations now of the turning point. Okay, so we found them from our differentiation process. But what we do not know, without the graph, we do not know if they're maximums or minimums. So let's go to the final step, step 4 now, and let's see if we can determine if they're maximums or minimums. So in step 4, find if max or minimums. We can clearly see it in this case, but as I said, in most of the questions you will not have the graph, so you won't know unless you sketch them yourself. You won't know if they're maximums or minimums. So we need to find the second differential now. So all we're going to do is take the equation 2 shown above and differentiate it again. So this is the second differential now. So d2y by dx squared. So again, it's standard form. I've got 3x squared minus 3. So differentiating that, 3x squared becomes 6x. And differentiating negative 3 with respect to x, that will disappear. Constants always disappear. So that's our second differential. What we need to do now is put the values of x into the second differential and find the value of the second differential. Don't forget, if it's positive, we've got a minimum. If it's negative, we've got a maximum. Okay, so that's all we're going to do is put the values of x in. So when x is equal, let's take the first value of 1, we can see that the d2y by the dx squared is equal to a positive value. I'm not bothered about its actual magnitude. It's obviously 6 in that case, but I don't care. It's a positive value, so that's a minimum. Okay, we can see that on the graph. When x is equal to 1, we've obviously got the minimum. And then taking the x is equal to negative 1, the d2y by the dx squared is equal to negative value. Again, not bothered it's negative 6, just a negative value. So therefore, that's a maximum. Okay, and that's all I need to do with the second differential. Just find the sense of the answer. If it's a positive value, it's a minimum. If it's a negative value, it's a maximum. And that's job done. That's all we need to do. Obviously, in some questions, the context there, so that those turning points would relate to like maximum velocity, maximum acceleration, whatever it might be. Okay, so the first thing I want to do is to practice this technique with you and let you have a go at this 4-step process we're going to use. Here are the tutorial questions that are now going to be considered. Consider question 1 and some of the equations in question 2. No answer is shown in the square bracket on the right hand side. So let's have a look at question 1. I'm going to get you going on question 1 and you can have a little play with question 2. And then what I would like to do before we finish the session is take you into some practical questions where you have to generate the equations again and then go on and solve for the second differential. So I'd like to just end with those if we can. So I'm going to try and keep it nice and structured here, go through our same sort of 4-step process. We're given the equation of y is equal to x squared minus 4x minus 1. We've got to find whether it's the maximums or minimums here. So in step 1, the first thing we do is differentiate the equation. So dy by dx is equal to, so standard forms here, x squared differentiates to 2x and negative 4x differentiates to negative 4. The constant will disappear. That's all from our standard tables. Step 2, we're going to equate the equation to 0. And again, if I just give them labels, I like to give them labels. That's equation 1, that's equation 2 in this case. So equate equation 2 here. Okay, so 0 is equal to 2x minus 4. Need to rearrange the equation. So 2x is equal to positive 4. So that gives us x is equal to 2 in this case. Check your rearrangement there, make sure you're happy with that. So x is equal to 2. So now we've defined our turning point in the x direction, but we need to know what it is in the y direction. So that's where step 3 comes into play. So step 3, find the y value. So using equation 1 here, just simply put the value of x into equation 1. So the y is equal to x squared, so that would be 2 squared minus 4 multiplied by 2 minus 1 in this case. So that's going to be 4, take away 8, looks like we've got a negative 5 there. So negative 5. So we now know our turning point coordinate. So that will be 2, negative 5. So that's where the turning point occurs in 2 dimensions. What we don't know without seeing the graph is whether we've got a maximum or minimum. So we need to find the second differential. So let's have a look at that. So step 4. Alright, so differentiating equation 2 in this case. So 2x minus 4 differentiated becomes 2. So the d2y by dx squared is equal to 2. That's a positive value. So therefore, if you were to plot this quadratic, that's what you would find. That's what it would look like. Alright, so that's the kind of thing we're looking at. That would be the positive 2 there. This would be the sort of negative 5 here. That's where a turning point would occur. Something like that anyway, that's what it looked like, okay? And again, that's job done there. Only one turning point in that particular case. And here's question 2. Question 2, we did quite a few questions here. So in the time we've got, I think A, B, and D and E maybe. So what I'll do is I'll go through question 2A with you. Okay, let's give it a question. So again, just trying to adopt the 4-step process we're going through. First thing is to take the information out of the question. Again, there's no need to rearrange or anything this time. You'll find that some of the questions you may need to manipulate the equation just a bit, maybe expansion of brackets or something like that, collecting terms together sometimes. In this case, that's fine as it's written, and then differentiate it. This is a similar solution to what we had before, actually, this one. Okay, solution for question 2. Question 2 part A there. Okay, so there's my solutions to question 2b, if that helps you at all. So don't worry if you don't want to use factorisation, just use the formula in question 2b, part 2. Sometimes the questions for this type of problem are given in a very practical context, and that's what example 2 is. We've got a small box to be made from a rectangular sheet of metal, and it's given some geometry in the question, so you've got the geometry given for the sheet of metal here, so that's the sheet shown there. And they're going to cut 4 square corners from the sheet. Each corner is labelled x by x, as you look at the dimensions here, x by x. We've got to determine the value of x that will give us the maximum volume of the box. Okay, so we're looking for a maximum in this case, and then we've got to calculate the maximum volume. So this is the question where you have to generate the equation first of all. Now the way these questions are normally worded is they give you the equation anyway. They say, show this equation. So if you cannot show it, which normally is about 2 or 3 marks, you can still use the equation to do exactly what we've been doing in the previous part of the session, all right? But there's an extra sort of 2 to 3 marks for showing how to generate the equation. So we're just going to take you through this example 2 here and show you what's going on. So we're talking about volumes here because it says in the question they want to find the maximum volume. So the hint would be you need the volume of a rectangular box here. So using the standard notation, that's breadth times length times the height of the box. The height in this case would be x. So BL and x is the formula using, sort of length times breadth times height kind of thing. Now from the geometry, this is how you've got to be sort of generate the equations. Dimension B is 2.4 take away twice x. Can you see that on the screen? It's 2.4. There's the 2.4, which is the total height there, and we take from that 2x because we've got corner x and corner x to cut from it. We're going to fold this box up. We're going to make this box from a flat sheet of metal here. So we're going to cut the corners x by x and then fold up. So that means the width B across here is 0.24 take away 2 times x. That's how we get this equation here for B. If we look at equation for L, this is the length of the box, so the length is here, then the length of the box would be 0.36, again take away 2 times x. So the length of the box is shown here, and that's sort of this dimension. That's the length of the box across there, and then the width of the box, the B, is that dimension there, if you see what I mean, when we fold it up. So again, that's quite thought-provoking, this to be able to generate the equations, but given the information, that's how you would form B and L parameters in terms of x. And then because the volume is the B times the L times the x in this case, we then multiply these together. So you'd multiply the B term there, multiplied by the L term there, and it's all multiplied by x. Okay, so that would give you an equation. It's a binomial expansion there, so even the expansion is not particularly easy to do. You've got to multiply this by this, and then this by this, and this by this, and this by this. Expand the bracket and then multiply the whole thing by x to form your equation. There's the full equation formed here in this equation 1. Okay, now you're back to where you were in the previous work. Now you've got to go through the process of differentiating the equation, equating it to 0, all the steps we did before. But that first part of the question is sometimes an additional part of the question they will ask you to attempt. Usually equation 1 is given anyway, and they say show this equation. So you get 2 or 3 marks for showing the equation. But the rest of the process there in the solution, the differentiating, that's all what we did before to find the second equation. The equating to 0, that's the same kind of thing. The solving the quadratic, in this case it is a quadratic that has to be solved using the formula. And then the solution goes on then to find the location of the volume given the value of x, and then find if they're maximums or minimums. You're looking for the maximum in this case. So the last part of the process is actually very similar to what you've already done. It's that first part where you've got to generate the equation. And purely for ease of reference, I've included an enlarged view of example 2, the application of turning points that may be easier for you to view. And for your reference, there is a further presentation that reviews differentiation applications of turning points in much greater detail, finding maximum volumes and maximum surface areas of various sections. So that concludes the lecture, which I hope has been of some use to you, and as always, thank you for viewing.